Refraction and Snell's law. As we saw in the electromagnetic waves unit, light slows when traveling through a medium. The index of refraction, n, of the medium is the ratio of the speed of light in a vacuum to the speed of light in the medium. So let's say, what's the n value of a vacuum? Well, the velocity of light in a vacuum is c, which would be c over c, which would be 1. However, for any other material, v is going to be slower than c, which means the denominator will be less than the numerator, giving us a value that is always going to be more than 1. So for water, the value is 1.33. For diamond, it's going to be 2.42. Light also sometimes changes direction when it enters a new medium. This is called refraction. The angle of incidence here is related to the angle of refraction here. When the light ray goes from less dense to a more dense medium, like from air into water, it bends towards the normal line, and the refracted angle is smaller than the incident angle. And when the light ray goes from a more dense material into a less dense material, like from water into air, it bends away from the normal line, and therefore the refracted angle is larger than the incident angle. There is an equation that dictates what these angles will be. Snell's law allows us to calculate the angle of refraction when light enters a different transparent medium. N1 sine 1 equals N2 sine 2. So what that means is that if you're going from air into water, N1 would be N for air, which is approximately 1. Sine theta 1 would be this angle here, the angle of incidence. That has to be equal to N2, so for water that would be approximately 1.3, times sine theta 2, so that would give you sine of the refracted angle. When light passes from air to a different medium and then back into air, the ray that enters the medium is parallel to the ray that exits the medium. Using geometry, we can find the linear displacement between the emerging ray and the incident ray if we know the angle of the incident ray and the thickness of the other medium. Refraction is why objects look weird if they're partially underwater. When a ray of light goes from a denser medium to a less dense medium, if the incident angle here is just big enough, the refracted ray will be parallel to the surface, so the refracted angle will be 90 degrees. This angle here, the incident angle, is called the critical angle. When the incident light ray is at this critical angle, that means that none of the light is able to escape the denser medium. So remember, if the incident angle was smaller, this ray would bend away from the normal. So as this incident ray goes this way, this refracted line goes that way. Eventually, it just goes straight across this way, and none of the light is going to go into the air. When the angle of incidence is larger than the critical angle, no light escapes the medium. This is called total internal reflection. So here, some of the light is going to be reflected back into the water, some will go through into the air. Here, all of the light is just going to go parallel to the surface. However, here, the angle is larger than the critical angle, therefore all of the light is going to reflect with an equal angle. None of it will refract through. Remember that light both reflects and refracts when hitting a surface or an interface. For example, see what happens to a ray of light as it goes from glass to water to air. So our incident rays here, when it hits this medium between the glass and the water, some of it reflects this way, some of it refracts through. And since it's going from densest to less dense, it's going to bend away from the normal. So see, this angle of incidence will be smaller than the angle of refraction here. Then it hits this interface between the water and the air. So some of it's going to reflect back into the water, some of it will refract through, and because it's going into a faster medium, Once again, it will bend away from the normal. This ray is going to go down here. It's going to reflect and refract, and since it's less dense into denser, it will bend towards the normal like that. So you can really trace these rays over and over again all throughout this drawing. A substance has an index of refraction of 2.42. What is the critical angle for that substance in a vacuum? We're going to use Snell's law to solve for the angle of incidence, this angle here. The angle of incidence will equal the critical angle when the angle of refraction is 90 degrees. Since sine of 90 degrees is 1, we can just take this whole term, make it 1. So therefore, we're solving now for theta 1. So we're going to divide both sides by n1. Then we're going to take the inverse sine, right? Because we have sine theta equals n2 over n1. Therefore, we take the inverse sine. So theta is going to be equal to the inverse sine shown here. Put that in your calculator and you get 26.5 degrees.